Hello, this is Mr. P, and today we're going to talk about two-dimensional vectors, or in other words, vectors in a plane. We're going to start with our definition of vector, which says that a vector is a directed line segment. Now, that's just different from a regular line segment that we saw in geometry, where you had a line that had two endpoints. Well, a directed line segment says that those two endpoints are going to be distinguishable. In other words, one of those endpoints will be the initial point, and the other endpoint will be the terminal point. Now, visually, we represent a vector with an arrow, and the initial point, let's call that point P, and the terminal point we're going to call point Q. So another way to think of a vector is they are directions from one point to another. So from the initial point to the terminal point, it'll tell you how to get from one point to the other. Now, with notations, there's going to be various notations you can use. I want you to be familiar with a lot of different notations. So naming vectors, one thing you can use is the endpoints themselves, and we can write vector PQ using this notation. It's the capital letter P and the capital letter Q denoting the points, and then the vector symbol is an arrow, but we usually don't write the bottom tail of the arrow because that'll go into whatever the letters are down here. So this is read literally as vector PQ. And just like in geometry, we can also use a lowercase letter to denote a side. We can use a lowercase letter to represent a vector as well. So if we wanted to use vector V, for example, we would have a lowercase v with the arrow on top of it. And this would be read as vector V. Now, when we want to break a vector down into its components, we usually talk about the horizontal component and the vertical component. And to do that, let's take P to be the ordered pair P1, P2. In other words, P1 is the x-coordinate of this point, and P2 is the y-coordinate of this point. Likewise, the coordinates of Q are going to be Q1, Q2. Well, the idea here is that we can write a vector in component form by, instead of describing that direction, we're going to say we can go horizontally in this direction and then vertically in this direction, and we'll arrive from the initial point to the terminal point, because those are going to be our directions. So we're going to think of the horizontal component and the vertical component. And when we set this up, we're going to look at the length of this side, because this turns out to be a right triangle. The length of this side is going to be the difference in the x values. And for this side, the length of the sides are going to be the difference in the y values. Now, these two sides themselves can be vectors as well. Let's say this is the x vector and this is the y vector. Now, when we write the component form, let's say vector v, we're going to use what are called angle brackets. These are the angle brackets. They look like a less than and a greater than symbol. And inside, we're going to make the calculation for the difference in x and the difference in y. Now, one thing to remember, and it's important in mathematics to be consistent with this idea, whenever you talk about the difference in mathematics, it's always going to be terminal minus initial. For example, if I'm running a booth and I start out with $5 and I do certain transactions during the day, and at the end of the day I end up with $7, you would say that the difference was $2, not negative $2. In other words, I do 7 minus 5, not 5 minus 7. So it's the money I ended up with at the end of the day, the terminal amount of cash, minus what I started with, which was the initial. So in mathematics, difference is terminal minus initial. So here, I want the x value of the terminal point, Q1, minus the x value of the initial point, P1. So difference in the x's, terminal minus initial. And then difference in the y's, again, terminal minus initial. And when we find those differences, those are going to be the lengths for x and y. So the horizontal component would be the x, the vertical component would be the y, and we say this is in component form. Now if we were to give this some numbers as a number example, let's say this length was 3 of this side, and the length of the vertical side was 2, then we could say that this was the vector 3, 2. And this is in component form using angle brackets. This says if I'm at point P, I go 3 horizontally, 2 vertically, and I arrive at point Q. This is the component form gives you both of the horizontals. We're going to see later another way to give directions is going to be the magnitude times the direction itself. So we can either go straight along the vector V, or we can go horizontally and then vertically. Now for notation-wise, angle brackets, not every textbook or every professor uses angle brackets. Some use the hat notation, and they would write the vector in this way. 3I hat plus 2J hat. The I hat stands for the unit vector horizontally, and the J hat stands for the unit vector vertically. So it's 3 units horizontally, 3 units vertically, and that would be your vector. Or you might see down the road, vectors could be written this way as well. I know a lot of graphing utilities like to use this notation as well. But mostly I'll be using angle brackets or the I hat. Now for standard position, one of the things that makes vectors so great to use is their versatility. I can take this vector and I can move it over here, and it's still the same vector. It still represents a magnitude, which is its length, and a direction. No matter where I place it, it's still that same magnitude, times that direction. Now, of course, if I rotate it, I'll have a different direction. That would be changing it, but translations do not change the vector, which means we can move them around to make it advantageous for our calculations. So one of the places we like to move it is what's called standard position. That's where our initial point is going to be at the origin, and that way our terminal point will just be out somewhere in one of the quadrants. But that's called standard position. Now when we talk about magnitude of a vector, we're talking about the length of the vector itself, and there's a notation for that. It looks like a double absolute value symbol, but it's read the magnitude of vector V. So the magnitude of vector V, like we said, is simply the length of the segment. So it should be no surprise that the formula for that is really just the distance formula. It's the distance from P to Q. So if you might recognize the distance formula here, the distance from P to Q, or since we introduced the X and the Y as well, in component form, it would also be the Pythagorean theorem, finding the hypotenuse of a triangle, of a right triangle that has legs X and Y. So whether you think of it as the distance formula or the hypotenuse of the right triangle, in either case it's going to be the length of that vector. Now unit vectors are vectors that have a magnitude of 1. They can be in any direction, but if they have a magnitude of 1, then it is a unit vector. Now 2 of them that we're concerned with today, 2 of them have a special meaning. The first is the I hat, which we saw up here. I hat is the horizontal unit vector. It has the components 1, 0. So you go 1 to the right, and then you don't go up or down. And likewise, the J hat is the vertical unit vector. That one you don't go left or right, but you go up 1 unit. So here, this is literally saying 3 times the horizontal unit vector, and then plus 2 times the vertical unit vector. And of course, a 0 vector is a vector with a magnitude of 0. It's just a point. You don't have any movement. That can happen sometimes when you're doing a vector addition or subtraction, and your result is a 0 vector. It means nothing actually changed. All right, let's look at a little bit about scalars. A scalar, and we're going to talk about scalar multiplication. We'll get into vector multiplication in the next section, but scalar multiplication is when you're multiplying a number. A scalar just means a number. It's going to be a number times a vector. And the geometric effect this has is that it will stretch the vector, but it does not change the direction of the vector, which is going to be very important to us. So let's take this vector here. This is it visually, and this is it in component form. Vector v is v1 comma v2. So this vector, if I were to multiply it by 2, 2 being our scalar, then geometrically I'm just taking this same vector that we have here, it's going in the same direction, but it's going to be twice as long as it used to be. So same direction, just twice as long. Algebraically, I can write this as 2 times vector v, and when it's in component form here, you can distribute the 2, so the vector is going to be 2v1, 2vu. I'm sorry, 2v2, I mean. So again, scalar multiplication just stretches the vector, it does not change the direction. Now vector addition, if we look at this in the right way, it's going to set up for things to be easier in the future. But for vector addition, we're combining 2 or more vectors to get a resultant vector. In this example, we're just going to do two of them. So here I'm going to use vector v is v1 comma v2, and vector u is going to be u1, u2. So there's 2 things I want to do here. First I'm going to do v plus u, and then I'm going to do u minus v. Okay, starting out with the v plus u, let's look at, for example, let's say this was vector v, and let's say this was vector u. They're both starting at the same point. And I want to add these 2 vectors. Let's say they're both in standard position. Let's say this is the origin. Then, and of course we're using no numbers here, so this is completely general to any vector we're talking about here. If I wanted to add them, then what we're going to do is what's called the parallelogram rule, or the head-to-tail method. Now the parallelogram rule says that I can take this vector and bring it over to here, which would make the initial point of this vector coincide with the terminal point of this vector, and by sliding this over, I get the resultant vector would be where I go from the beginning to the end. In other words, this is saying travel along v and then travel along u if you're doing head to tail. So here, starting at v, I travel along v, and then I go in the direction of u for the length of u. So I can just take this vector, shift it over here, and make that u, or make a copy of it like I did. Likewise, we could have also traveled along u and then traveled along v and ended up at the same point. So in either case, whether we're in v then u or u then v, the resultant vector is going to be the vector that gets us from the beginning of the first, from the initial point of the first vector to the terminal point of the last vector, even if we had 5 of them that we're adding together. So this vector here is the resulting vector, and let's call that vector r. And the reason it's called the parallelogram rule is, notice that we've created a little parallelogram here, and the diagonal of the parallelogram is your resultant vector. And also this shows us a property we're going to get to later, that it doesn't matter whether you do v plus u or u plus v, the commutative property of addition is still going to hold with vectors. Now for an algebraic approach, we could have done this algebraically by simply, since we have addition here, we can add the units or add the components. So here it's going to be, for the horizontal, I have v1 and I have u1, and I'm simply going to add those together. So it's v1 plus u1, and then for the verticals, it's going to be v2 plus u2. So this would be the resulting vector algebraically. Now for subtraction, this is where you have to be careful, and there's a lot of misconceptions sometimes. Like if we have the same two vectors we're starting with, let's say we wanted to do u minus v. then that would be the difference between the two vectors. So if we start at the same point, and this vector goes to here, and this vector goes to here, then the difference of the two vectors is simply going to be the distance between the two terminal points. Now, when we add or subtract vectors, the result is going to be a vector. It's going to be a resultant vector. So when I do the vector to these two terminal points, then am I going from v to u, or am I going from u to v? That's the question that's often misunderstood by students. And if we go back to what we said about the right way to think of a difference in mathematics, a difference is terminal minus initial. So if I look at here, terminal minus initial would be the difference. So u is going to be the terminal endpoint, and v is going to be the initial endpoint. So the correct way to do this would be the vector that's heading downward, not upward. A vector that was going upward would be v minus u instead of u minus v. Now notice if we copy those two vectors to make our parallelogram just like we did before, we still recognize the parallelogram rule. It's just that the other diagonal is what gives you the difference. If it's going down, it's u minus v. If it's going up, it's v minus u. And this diagonal was v plus u, or u plus v. Either way, it's the same one. All right, now let's also look at this geometrically. I don't want you just to memorize that it's terminal minus initial without seeing another way to visualize it. So let's take it sort of literally. Let's start with u. We're going to travel along u, and we're going to do a head-to-tail method here. So we're traveling along u, and then head to tail is what we do when we're adding. So this would be the same as we add a negative v. Well, the negative of a vector just means that we change the direction. So if we look at v, v goes from here to here. So if I change the direction, then negative v would be the same slope, so to speak. It's just its direction would be a 180 degree or pi radian turn. It's going in the complete opposite direction. Same magnitude, just opposite direction. And now we can think of this as u plus a negative v. So if I travel along u and then do a negative v, then my head to tail method, I'm starting here, I'm ending here, and that would be the vector that is the result of u plus negative v. And notice how in both cases we get the same vector. So whether you think of it as terminal minus initial, which will be a good way to think of it, beneficial in the future, or whether you simply think of it as u plus a negative v, in either case you're going to get the correct resultant vector. All right, let's look at one more at the component form and the magnitude. Look at a couple examples here. We have two vectors, vector v and vector u, and for each of these we're being asked to write them in component form and to find the magnitude. This vector starts at 1, negative 1 and ends up at negative 3, 6. So what we're going to do here is we're first going to find the component form, and I'm going to use the angle brackets. I like that notation. Now we're going to find the difference in the x's, and this is where it really helps to know terminal minus initial, because to do 1 minus a negative 3 would be incorrect. We want negative 3 minus 1 because it's the terminal point's coordinate minus the initial point. So it's negative 3 minus 1, terminal minus initial. Likewise, it's 6 minus a negative 1. And of course, that cleans up to be negative 4, 7. So the vector negative 4, 7 would be the this vector in component form. Now for the magnitude, we're going to find the magnitude of v. And once you have it in component form, you can think of this as a right triangle with this side being 4 and this side being 7 units. And that positive or negative actually doesn't matter in this application because notice we're going to square it anyway. But technically it is negative 4 squared plus 7 squared. You're squaring the two sides, add the squares together, and then take the square root. That would be the length of the hypotenuse. So this turns out to be the square root of 16 plus 49, or in other words, square root of 65. And you do want to leave it as a radical because that is the exact magnitude. If you put that in the calculator and get a decimal, then you've now made an approximation, you've introduced error. Alright, for part B, we're going to do the same thing with part B, but this time our vector is in standard position. We're going to see this turns out to be a lot easier. If our vector is in standard position, then the initial side is 0, 0. The initial point, I mean, is 0, 0. So for our difference here, it would be 3 minus 0 and 4 minus 0. So we're just going to get the same in a vector, a component form. We're going to get the vector is going to be the same numbers as that terminal point. And this is going to happen anytime your vector is in standard position. Now for the magnitude, this is where I try to advocate working smart rather than hard. If you recognize that geometrically this is going to be a triangle with sides 3 and 4, then hopefully you remember the 3, 4, 5 triangle, which means I already know that that hypotenuse is going to be 5 units, so that's my magnitude. Yes, you can go through 3 squared is 9, 4 squared is 16, add them together, you get 25, square root of 25 is 5. The numbers do check out. But if you can recognize a 3, 4, 5 triangle or other Pythagorean triples like 5, 12, 13, 7, 24, 25, or even 8, 15, 17. Those are some common ones. Remember, plus any multiples of those as well. So 6, 8, 10 would be a Pythagorean triple just like 3, 4, 5. So those can be time savers when we can work smart rather than hard. But the important thing here is to recognize that when the vector is in standard position, the component form is the same as the terminal point. So looking back at this first one, rather than go through these calculations, I could have just moved this vector so that it's in standard position. And notice when I did that, this becomes its terminal point, which is negative 4, positive 7 would be the new terminal point. Negative 4, positive 7. Alright, let's look at some properties. And all of these properties are going to pretty much go right in line with the properties you already know for algebra, with the exception of the last one. But starting out with, and this one we already saw the geometric reason why, vector u plus vector v is going to be the same thing as vector v plus vector u. This means that the commutative property of addition is still going to hold for vectors as well as in algebra. Now also, for association, if I have u plus v, now to get through these a little quicker, I'm just going to say u and v rather than vector u, vector v every time. But u plus v and then plus w is going to be the same thing as if I did u plus and then v plus w being associated. So the associative property of addition will also hold for vector addition as well. Then we want to look at our identity element. So u plus a 0, or a 0 vector, is going to simply be the same thing. That's the identity property of addition still holds for vectors. Additive inverses also hold. Remember, u plus a negative of u. Remember, a vector that has a negative sign in front of it just means it's in the opposite direction. So if I go a certain distance in a certain direction, and then I go that same distance in the opposite direction, then I end up exactly where I started, which is the 0 vector, which means no change. Also, if I have a scalar times a vector, then you can think of this as distribution, but it's really the associative property of multiplication. I can either multiply the scalar times a vector and then the result times a scalar, or multiply the scalars together and then multiply the result times the vector. So the associative property of multiplication still holds. For distribution, I have two versions for you. Let's say we have c plus d, which are scalars, and then times vector u. Now you can distribute that vector, and notice how when I do that, I'm getting scalar times vector in each one. We'll cover vector multiplication in the next section. But we can distribute from the right, just like you can distribute from the left, and u times c is going to be cu. We usually write the scalar first, then the vector. So cu plus du. So the distributive property does hold for vectors. And that also works if you have a scalar distributing into a sum of vectors. Again, notice that's scalar times vector, so it's going to be cu plus cv. We already did the identity element of addition. Well, there's also an identity element of multiplication, which would be 1 times any vector is itself. And the zero product property, if I have 0 times a vector, then the result is going to be 0. 0 times anything is going to be 0. And the last one, which might be new to you, says that if you have the magnitude of a scalar times a vector, if you wanted to factor that scalar out, you can do that. However, when you do that, you must take the absolute value of that scalar. So yes, you can pull the scalar out of that magnitude, but you must introduce the absolute value. The reason is this left side here, the left-hand side, represents magnitude, which is always going to be non-negative. Magnitude could be 0 or it could be positive, but it can't be negative. So if I pull that c out in front and c is allowed to be a negative number, then the result here, when I multiply it times the magnitude, which I know is going to be non-negative, so a negative times a non-negative is going to be negative or 0. And we can't have that happen. So that's why this is the absolute value of c. That way we know c will be non-negative and this will be non-negative. So the result of multiplying the two together will be non-negative. All right, let's look at some example problems, see the skills that we need to do. And I'm going to show two different notations just so that you see the differences, which one you want to go with, because different books will use one notation or another notation depending on the author or the professors. But let's say v is the vector 2i hat plus 3j hat, or in other words, the vector 2, 3. And w is going to be the vector 3, negative 4. So given those two vectors, we want to find, first of all, what is 3 times v. And that would, in hat notation, that would be 3 times 2i plus 3j. And that if we distribute this, of course, using our property from the last page, then we'll have the resulting vector would be 6i hat plus 9j hat. You can also do this with the angle brackets, which is actually the one I prefer. So 3 times 2 comma 3. Again, think of this as distribution. It's simply going to be still in angle brackets, but 6 and 9. So this one or this one, they both represent the same vector. Different notation for the same vector. Okay, let's say we had 2v minus 3w. Well, we're going to first do it with the I hat notation. This is going to be 2 times vector v minus 3 times vector w. And we're going to start out with our distribution. So 2 times 2 is 4. 2 times 3 is 6. But this is where you have to be careful. This is where the mistakes are normally made. Negative 3 times 3 is negative 9. Usually students get that one. But then negative 3 times negative 4 is a positive 12. Be careful with your signs. Now, just like algebra, we can combine like terms. So we have the i's, we have a positive 4 and a negative 9. Combine those, you get a negative 5. And for the j's, a positive 6 and a positive 12 give you a positive 18. So that's in the I hat notation. Or, I'm sorry, in the hat notation. Now for angle brackets, we're going to start out with 2 times vector v and then minus 3 times vector w. And I'm going to distribute on the first one, it's 2 times 2 and 2 times 3. That gives me 4 times 6. But I'm going to leave the negative here, and I'm only going to distribute the 3. I'm only going to distribute the magnitude there. So we have 3 times 3 is 9. 3 times negative 4 is negative 12. And now I can go ahead and do the operation. So this is going to be 4 minus 9 is going to give me a negative 5. And then this is the one to be careful of. It's 6 minus a negative 12 gives you positive 18. So once again, whether you have it in this format or in this format, it does represent the same vector. All right, to find the magnitude, let's look at vector v is this vector here. I'll start out with the hat notation. We want the magnitude of this, which means I'm simply going to square these, and when I square them, I can ignore the I hat or the j hat. And I'm going to square them, add them together, and then take the square root. So it's going to be the square root of 2 squared plus 3 squared. 2 squared is 4, 3 squared is 9, add them together you get 13, so it's the square root of 13. And with the angle bracket, although we start out with the angle bracket notation rather than the hat notation, our next step is exactly the same. It's still the square root of 2 squared plus 3 squared, so we still get the same result. So either way you want to do these is fine. All right, let's look at unit vectors. The next formula it often looks intimidating, but it has a very geometric meaning behind it. In other words, first I'm going to show you this is the formula for a unit vector. And it might look weird at first, but if you think about it, it really makes sense. A unit vector is simply a vector that's in the same direction as the vector you have, only it has a magnitude of 1. So we're not changing the direction part, we're taking whatever its length is, and we're multiplying it by something to change the length to 1. So if you take any number, 4, 5, 7, if you multiply it by 1 over that number, then you're going to have a result of 1. So x times 1 over x, as long as x is not 0, x times 1 over x is going to be 1. So in other words, we're dividing by the magnitude. If I take vector v, whatever that vector is, if you divide it by its own magnitude, the result will be a vector that has the same direction. Sorry, we haven't changed the direction. However, by dividing by the scalar, because the magnitude is going to be a scalar, we're simply compressing it down to a unit vector, a vector of magnitude 1. Another way you might see this written is if you take the denominator here and bring it to the other side, you'd have vector v is the magnitude times the unit vector. So this would be another way to write the same formula. And this has another important meaning as well. This one, when you see it, you should think, well, if you take any vector and divide it by its own magnitude, you'll have a vector that has a unit length, that has a magnitude of 1 in the same direction. Or over here, this idea says that any vector is going to be a product of its magnitude and its direction. And especially in science, you see this one used more in science because you talk about a force, the amount of that force is going to be the magnitude, and then the direction in which that force is applied, that's going to be your direction, which is represented by that unit vector. So a vector is simply magnitude and direction. So let's look at some examples here. We're going to find the unit vectors for one of them in hat notation, one in angle brackets. So 4i minus 3j, I'm going to take the original vector itself. I'm going to use this formula here. The original vector itself divided by its magnitude. Well, its magnitude is going to be the square root of 4 squared plus a negative 3 squared. In other words, this is my calculation for the magnitude. 4 squared is 16. Negative 3 squared is 9. If I add those together, I get 25. So I want the square root of 25, which is 5. Now, Here again, if you recognize that you have 3 and 4 are the legs of this triangle, if you think of this geometrically, then if you recognize a 3, 4, 5 triangle, then you really could have jumped from this step to this step. Once you get used to working with vectors, you can just look at this and already know 3, 4, 5 triangles, so that magnitude is 5. You can jump right to here. And now, we don't want to leave our answer in this form because we do want to break it up into a horizontal and a vertical. So this ends up being 4/5 I hat minus 3/5 j hat. Alright, for the angle bracket version, again, it's going to be the vector itself divided by its magnitude. And of course, we can do the square root of the x component squared plus the y component squared. When you do that out, you're going to find it's the square root of 169, which is 13. But once again, if you recognized 5, 12, 13 as one of your Pythagorean triples, then you could have jumped right from this step to this step. And now once we have that, we're simply going to break it up. It's going to be in angle brackets, negative 5/13, comma 12/13. Alright, the next thing we want to look at is direction angle. For a direction angle, we're going to start with our unit circle. And we're going to say, let's say we have a vector, and we're going to call this vector v. We're going to derive a formula to be able to find out what is the direction angle of any vector. And by direction angle, what we mean is if I put my vector v, if I put it in standard position, which it's in, its initial point is at the origin, then the angle it creates with the positive x-axis, that theta there, that is going to be our direction angle. So let's do a little geometry here. Let's take the unit circle here. And I'm going to drop a perpendicular from where this vector intercepts the unit circle. And I'm going to call the vector that goes from the origin to the unit circle along the exact same direction. In other words, I'm going to consider this vector here. And that vector I'm going to call vector u, because it is a unit vector, by the way. The radius of the unit circle is 1, and it's also in the same direction as v. So it is the unit circle, it is the unit vector for v. But also, since I know my unit circle, I know that this side of the triangle, because I've now created a right triangle, this side of the triangle is the cosine of theta. You know, the adjacent side of any right triangle is going to be the hypotenuse times the cosine, but our hypotenuse is 1 because we're in the unit circle, so it's going to be x is cosine theta, and of course y is sine theta. So now let's create some notations. I'm going to try to write u and v in multiple ways and then do some substitutions. So one way I could write u is I can say u is x and y. But since we already discovered that x is cosine, y is sine, then I can say vector u is really cosine, which is x, comma sine of theta. Although I'm not saying the argument, you always do want to write down your argument. So cosine of theta, sine of theta. So I can write it that way in angle bracket notation, or I could write it in hat notation, where vector u is cosine theta I hat plus sine theta j hat. These two both mean the same. Alright, so that's our unit vector. Let's look at our actual vector itself. Let's say that our vector is, if we were to break it down in component form, is A and then B is the vertical component. So A times I hat plus B times j hat. That's going to be our vector V. The idea that a vector, and this is our formula from the previous slide, our vector is going to be the magnitude times the unit vector. We're just taking that idea from the last slide. So the magnitude times the unit vector means it's going to be the magnitude times, now we already have a an expression for the unit vector, so I'm going to make that substitution. So magnitude of v times that is going to be our vector v. And then I'm simply going to take that magnitude, which is a scalar, by the way, so I'm going to distribute that scalar. So vector v is going to be magnitude times cosine theta I hat plus the magnitude times sine theta j hat. All right, so we have different ways we can write u. We have different ways we can write v. Now, coming down to our direction angle, we want to find some way to get our theta. So let's say I look at the tangent of theta. I want to consider the tangent of theta. And we can see visually tangent is going to be opposite over adjacent, which is sine over cosine, or hopefully you remember the fact that tangent is always sine over cosine. And now I can write it sine over cosine if I'm looking at the red triangle. But if you consider, let's drop a perpendicular here, if you consider the blue triangle, that theta is still going to be the same angle, so I can think of it as this over this, or this over this. So it would be sine theta over cosine theta if I'm looking at the red triangle, and it would be the length of this side, which is the magnitude is the length of the hypotenuse, the magnitude times the sine of theta, over the magnitude times the cosine of theta. And notice how if we compare this result to this, then we can see that magnitude of v times the sine of theta, that right there is what b is. Notice how this is the coefficient of j hat, b is the coefficient of j hat, so this expression in the numerator is b, and likewise this expression in the denominator, which is the coefficient of I hat, is the same as a. So this is really just b over a. And this gives us a way to find theta. Our formula is going to be that the tangent of theta is simply b over a when this is our vector. Given any vector, if it's in component form, then the tangent is going to be your vertical component over your horizontal component. Which should make sense because you can also think of this as rise and run, and since tangent is the same thing as slope, slope is going to be rise over run. But I did want us to derive it, officially, so that you can see where it comes from. So if you're given a vector, you simply are going to use this formula to be able to find the direction angle, which is your theta. Now, you still need, of course, take the arctangent of both sides. That way you'll have theta equals the arctangent of b over a. But for that, we're going to use some examples. We'll see that with some numbers. And actually, let's do that right now. We want to find the direction angle for these two vectors. And the important thing to remember here is you always have to be aware of which quadrant that you are in. Because sometimes when you do, especially when you do these on the calculator is going to give you an answer, and that might not be the answer you're looking for. You want to always make sure that you're in the quadrant you mean to be. So part of your steps, part of your work should be to list what quadrant you're in right off the bat. Now here, this vector, if it's in standard position, then the origin is where the initial point is, and the terminal point goes in a positive direction and a positive direction. Well, that'll put it in quadrant 1. That terminal point will be in quadrant 1, so theta will be a quadrant 1 angle. So now we know that the tangent of theta is simply going to be b over a, so it's the vertical component over the horizontal component, which is 2 root 3 over 2. The 2's cancel out, so it's simply square root of 3. But I don't want tangent of theta, I want theta. So theta, I take the arctangent of both sides, and I'm going to get theta is equal to the arctangent of the square root of 3, which of course, hopefully you know by now, is 60 degrees. So theta equals 60 degrees. Sorry. All right, now for our next problem, this is the one where you have to be careful because this is from the origin. We're going -3 and then -4. So that's left and down. That's going to put us in quadrant 3. So that's something I'm going to write it down because that's going to come into play later. So for tangent, we're going to say the tangent of theta is going to be the b over a, so it's the coefficient of j hat, which is -4, over the coefficient of the I hat, which is -3. Of course, the negatives can cancel, giving you just 4/3. And of course, I want to take the arctangent of both sides. So theta equals the arctangent or inverse tangent, whichever way you like to say it. But theta is going to be the arctan of 4/3. Now, that's not one of our special right triangles, so we need to do that in the calculator. We're going to do this one in degrees. So if you're in degree mode and you put in arctan of 4/3, it gives you back 53.1, etc. However, that is not the correct answer. Because notice right here, we said theta is in quadrant 3, and this is a quadrant 1 angle. So I don't want this answer, I want the other answer. Remember, when you take arcsine, arccosine, arctangent, the calculator is going to give you only one of the two possible answers. So to find the other answer, the adjustment depends upon which inverse trig function you're doing. For tangent, the adjustment is pi plus your first answer gives you your second answer, which I'm going to call theta prime. Or if you're dealing in degrees, this is if you're in radians. If you're dealing in degrees, then it's 180 degrees plus your first answer gives you your second answer. And that should actually be not with the prime. So 180 plus theta will give you that theta prime, which is your other answer. And that's because pi radians is the same as 180 degrees, of course. So using the degree version, I simply add 180 to 53, and that'll give me that theta prime is approximately 233.1. Now, remember your calculator adjustments, I'll mention them here just so I don't leave them out, is for sine, whatever your first answer is, it's going to be pi minus your first answer gives you your second answer. And for cosine, it's going to be 2 pi minus your first answer gives you your second answer. But since we're dealing with tangent, it's going to be pi plus your first answer gives you your second answer. All right, and with that, we are done.